I want to start today with a number, a very specific, very small number. 300 milliseconds.
It sounds like nothing, right? Barely a blink of an eye.
It really is, but in the world of the human brain, specifically when it comes to language, that tiny fraction of a second is, well, it's everything.
Yeah, it's the difference between silence and speech.
Exactly. There was this famous experiment back in the 70s by a researcher named Marsland Wilson. He wanted to sort of push the human brain to its absolute limit.
Right, this is the classic shadowing task.
Yes. So he plays a recording of someone talking, just a continuous stream of normal speech, and he asks people to repeat it back word for word as they hear it.
And the catch is, they have to do it as fast as humanly possible.
As fast as possible. And the results were honestly kind of unnerving. You'd expect a significant delay. You have to hear the word, process it, understand it, and then speak it.
But people could do it with a lag of only about 300 milliseconds.
It's practically instantaneous.
Which implies something incredible about how we process the world. I mean, it means that before a word has even finished leaving my mouth, your brain has likely already identified it, understood its grammatical role,
And send instructions to your own mouth to say it back. It feels like magic.
it really does.
It feels like telepathy.
But today, we're going to find out it's actually mechanics. We're doing a deep dive into syntactic parsing.
Which, I admit, sounds a bit dry. Parsing. It sounds like something a computer does to a spreadsheet in a basement somewhere.
I thought the same thing, but it's actually the high-stakes operating system of your daily life. It's the answer to the question. How do we take a stream of noise and instantly turn it into a structured, meaningful thought? And maybe more importantly,
Why does that system sometimes crash so spectacularly?
yes, and the research we're looking at suggests that to get that 300 millisecond speed, the brain has to cut corners. It has to make bets.
And sometimes it loses those bets. So let's unpack the core concept here first, which is incrementality. I love this word. It basically means we humans do not have the patience to wait.
We really don't. You might think the logical way to understand a sentence is to wait until the speaker stops, look at all the words, and then figure it out.
That would be the safe way.
The safe way. But we don't do that. We are building the plane while we are flying it.
So we interpret every single word the moment it hits our ears.
Immediately. We are constantly building a mental tree of relationships in real time. We don't wait for the punctuation.
But because we're moving so fast, we are vulnerable to being led into a trap.
Which in psycholinguistics, they call the garden path effect.
And honestly, looking at the research, it seems like most of what we know about how the brain works comes from studying those moments when it gets totally confused.
The oops moments, that's where the science happens.
So I want to try this on you. I know you know the science, you've probably read these papers, but let's see if your brain still trips.
All right, get me.
Listen to this sentence. The evidence examined by the lawyer turned out to be unreliable.
Yep. Even knowing it's coming, I still feel it.
You feel that little speed bump right in the middle, that jolt.
It's a distinct mental jolt. It's like stepping off a curb you didn't know was there. When you say the evidence examined, my brain instantly decides, okay, the evidence is the doer.
Right. The evidence is examining something.
Yeah, maybe it examined the crime scene or a bug under a microscope.
But then I say, by the lawyer.
And my mental structure just collapses. I hit a wall. I realize, oh, wait, the evidence didn't examine anything. The evidence was examined.
You have to stop, tear it all down, and build a new one.
Exactly. I had to rebuild the mental tree where evidence is the passive object, not the active subject.
That crash, that little moment of panic is the garden path. And this phenomenon is actually the battleground for a huge debate in cognitive science.
It really is. It's the debate between the modular view and the interactive view.
Or to put it simply, is your brain a rigid, rule-following robot, or is it a chaotic gambler?
I like that. Let's start with the robot. This is the garden path theory, championed by a researcher named Lynn Fraser.
Back in the late 70s.
Right. So Fraser's argument is that the brain is modular. It has a specific syntax module. Let's call it the grammar department. And this department is fast, dumb, and very, very bossy.
Fast and dumb is a great description. The idea is that this module draws the structure of the sentence first.
Before it even thinks about what the words mean. Precisely. It doesn't care about context. It doesn't care about logic.
It doesn't care if evidence has eyes.
Nope. It just looks at the word categories, noun, verb, preposition, and connects them in the simplest way possible. Fraser called this principle minimal attachment.
The laziness principle.
Essentially, yes. The brain chooses the structure that requires the fewest branches on the tree. There's a key example in notes. The spy saw the cop with binoculars.
Okay, classic ambiguity. Did the spy use binoculars to see the cop? Or did the spy see a cop who happened to be holding binoculars?
Now, if you ask the grammar department, there's only one answer.
The first one. The spy used the binoculars.
Right. Because attaching with binoculars directly to the verb saw is structurally simpler. It requires fewer nodes in the diagram. So the brain immediately assumes the spy is the one using them.
And it doesn't even consider the other option until later.
Not at first. It just grabs the simplest version because it's faster. If it turns out later in the story that the cop was the one holding them, then you have to go back and reprocess.
Your first instinct is always simplicity.
Always.
There's another rule this dumb robot follows, which I find even more relatable. It's called late closure.
Ah, yes. This explains why we all stumble on sentences like this one. When Mary was knitting, the socks fell to the floor.
I tripped on that just reading it in our notes. When Mary was knitting the socks, that feels like a complete thought.
Right. You want the socks to be the thing Mary is knitting. And why? Because of late closure. This rule says, basically, if you get a new word, attach it to the phrase you are currently working on.
So my brain is working on the phrase knitting. I hear the socks. I just grab them and stick them on.
It's like a greedy algorithm.
Mhm.
It grabs the nearest available slot, but then you hear the word fell.
And now you have a problem. When Mary was knitting the socks, fell. It just doesn't work.
Right. You realize the socks actually needs to be the subject of the next part of the sentence.
But the robot already grabbed them.
Exactly. And that's the modular view in a nutshell. We prioritize speed and simplicity above all else. Structural guess first, meaning check later.
It feels a bit inefficient, doesn't it, to make mistakes just to go fast?
Well, it's efficient 90% of the time. Most sentences are simple. But there is a scenario where this need for speed creates what looks like genuine anxiety in the brain. We need to talk about gaps.
This is the active filler strategy. It sounds like dentistry.
It does. It deals with sentences where things move around, like in questions.
Mm.
If I say, which girl do you believe John loves?
Okay, let me think. Which girl is at the front of the sentence? But grammatically, she's the object of the verb loves. She belongs at the end.
Right. In linguistics, we say which girl is a filler that has been moved, leaving behind a gap where she technically belongs.
So the listener has to hold which girl in their short-term memory until they find the spot where she fits.
And the brain hates doing that. It's like holding a hot potato. The active filler strategy says that when the brain identifies a filler, it becomes desperate to dump it into a gap as soon as it possibly can.
It wants to get it off the to-do list, even if it's the wrong gap.
Sometimes, yes.
Yeah.
We see this urgency across languages. In Dutch or German, for instance, speakers find subject-relative clauses easier to process than object-relative ones.
Why?
Simply because the gap appears sooner. They can put the hot potato down faster.
So that's the modular view, a fast, rigid system that loves the simplest path, meaning be damned. But surely we aren't that blind. If I say something that makes no sense, doesn't my brain stop the robot?
That is the big question. And that brings us to the challenger, the interactive or constraint-based models.
Okay, this feels more like the chaotic gambler side of things.
It's definitely more complex. Researchers like McDonald and Tannenhouse argue that the brain isn't a factory line where station A does grammar and station B does meaning. They think it's a free-for-all.
A courtroom where everyone shouts at once.
Or a gravitational field. One researcher, Tabor, uses this metaphor of attractors. As you hear a sentence, your brain is being pulled in different directions all at once. Syntax is one pull, but meaning is another, frequency is another, context is another.
And the strongest pull wins.
Exactly. So let's look at the evidence for this. If the interactive model is true, then meaning should be able to prevent us from getting garden-pathed.
Let's go back to the lawyer example. The defendant examined by the lawyer. That's ambiguous because the defendant is a person. They could examine something, so it's reasonable to get confused.
Correct. But what if I swap it? The evidence examined by the lawyer turned out to be unreliable.
Evidence is an inanimate object. It can't examine anything. It doesn't have eyes.
Right. So if the interactive model is correct, your brain should immediately scream, impossible. It should use that semantic knowledge to block the wrong pass. You shouldn't trip.
I did trip. When we started, I admitted I felt the bump on that exact sentence.
And that is the problem. The data is messy. Some studies show that using inanimate objects reduces the confusion, but it rarely eliminates it. We still see that little stumble.
Which suggests the robot is still in charge.
Or that the robot is just faster. There's fascinating evidence from brain scans ERPs. A researcher named Hegort found that when you hear a semantic error like the bread was crying, the brain fires a specific signal, an N400.
An N400 sounds like a sci-fi robot name.
It's just a specific wave of electrical activity. Think of it like a semantic fire alarm. But if you hear a grammar error, the brain fires a totally different signal, a P600. That's the structural burglar alarm.
So the brain has a grammar alarm and a meaning alarm, and they're wired separately.
It seems so. And crucially, the grammar alarm often rings first. This suggests that while meaning can influence us, it might be a split second too slow to stop that initial dumb structural guess.
Okay, but we aren't just reading isolated sentences in a white room. We have context, we have a world around us, and this is where the referential theory comes in, the two wives scenario.
This is one of my favorite counter-arguments to the pure modular view. It shows how the real world changes our grammar preferences.
Walk us through it.
Okay, imagine I tell you, the psychologist told the wife that he was having trouble with her husband.
Standard sentence, sounds like a normal therapy session.
Right. Minimal attachment, loves it, simple structure. But now try this version. The psychologist told the wife that he was having trouble with to leave her husband.
Whoa, that is clunky, the wife that he was having trouble with. My brain really did not want to go there.
It feels wrong, doesn't it? But researchers Crane and Steedman argue that this isn't just about grammar. It's about parsimony, making the fewest assumptions about the world.
What do you mean by that?
Well, the first sentence, told the wife, assumes there's only one wife in the room. It's a simple world. But the second one, the wife that he was having trouble with, that implies there are multiple wives present, and we have to specify which one.
Which wife? Oh, the one he's having trouble with.
Exactly. And since we usually assume people only have one wife, your brain rejects the sentence because the context implied by the grammar feels weird.
So if we change the context...
If you set up a story where there are two wives in the room, very dramatic therapy session maybe, then suddenly the complex sentence becomes easy because now you need that complexity to distinguish between the women.
The context justifies the grammar. The brain isn't just counting nodes on a tree, it's asking, does the situation require a complex description?
Precisely. And Tannenhaus took this a step further with his visual world paradigm. He actually tracked people's eyes while they listened to instructions.
This is the apple on the towel study, right?
Yes. So he puts a real apple on a towel and another apple on a napkin. Then he says, put the apple on the towel in the box.
Now, grammatically, that's ambiguous. Does it mean place the apple onto the towel? Or does it mean take the apple, which is currently on the towel?
If you can't see anything, your brain assumes the simple one. Put it onto the towel. But because people could see two apples, their eyes immediately went to the correct one. They didn't get garden pathed.
The visual context overrode the grammar preference instantly.
Instantly. That is huge. It means our eyes are cheating for our ears. We use the physical world to hack our language processing.
We use everything available. Visual cues, context.
Even word order to predict information. In Finnish and German, they found that changing the word order signals whether a noun is new information or old information.
So we are prediction machines. We aren't just reacting, we are anticipating. But all this, building trees, checking context, looking at apples, it has to cost something, right?
It costs memory.
Right.
We have a limited amount of RAM in our heads. This is what Gibson's syntactic prediction locality theory is all about. It's a fancy way of saying parsing is a resource management game.
We're running out of memory fuel.
Think about it. You have a storage cost, holding a prediction in your head, like that hot potato filler. And you have an integration cost, the energy it takes to connect a new word to an old one.
And distance is the enemy here.
Distance is a killer. If I say the dog that the mouse ran from chased barked.
Nope. My brain just melted. I'm sorry.
It's grammatically correct. But the distance between the dog and barked is just. It's bridged by too many other nouns. Your system freezes.
You have too many open applications.
Exactly. And when the system freezes or when it gets confused, we assume we go back and fix it. We assume that if we reread the sentence, we get the right meaning.
And this brings us to the most unsettling part of our deep dive. What if we don't?
This is the good enough representation.
And honestly, this explains so much about internet arguments.
It might. This comes from a study by Christensen and colleagues. They gave people a garden path sentence like this. While the man hunted the deer that was brown and graceful, ran into the woods.
Okay, let me parse that slowly. While the man hunted, the deer paws that was brown and graceful ran into the woods. So the man was hunting, and a deer ran into the woods.
Right. Grammatically, the deer is the subject of ran. It is not the object of hunted. The man was just hunting in general, not hunting that specific deer.
Okay, I get that. I can see the structure now. I fixed my mistake.
So they asked readers, did the deer run into the woods? Everyone said yes. Then they asked, did the man hunt the deer?
And people said no, right? Because they figured out the sentence.
They said yes.
Wait, what? So they thought the deer ran into the woods and that the man hunted it, even though that defies the grammar they just figured out.
Yes. They held two contradictory realities in their heads at the same time. They correctly analyzed the second half of the sentence, but they refused to let go of their first incorrect guess.
So we don't actually delete our mistakes.
We don't. We just clean them up just enough to keep moving. The initial misinterpretation just lingers. Our understanding is just good enough.
That is terrifying. It means I might be walking around with a half-baked understanding of half the things I read, contracts, emails, news. I mean, how many times have I read a complex sentence and just thought, yeah, I get the vibe, and moved on?
It gets worse. Sometimes we essentially hallucinate grammar to make things make sense.
Hallucinate grammar.
Ferrer calls it the NVN strategy. Noun, verb, noun. We are so addicted to the pattern of actor does action to object that we will force sentences into that mold. If I say, the dog was bitten by the man, for a split second, your brain might actually register that the dog bit the man.
Because that's what usually happens. Dogs bite men.
Right. We rely on these heuristics. But look at the study by Kim and Osterhout. They gave people the sentence, the hearty meal was devouring.
Whoa, meals don't devour, they get devoured. That's a meaning problem.
Obviously. But here's what the brain scans showed. When people read devouring, their brains didn't trigger an N400, the meaning alarm. They triggered a P600.
The grammar alarm? Wait, why? Why is syntactic error? The meaning is what's wrong.
You would think so. But the brain wanted meal to be the agent so badly. It wanted to follow the structure so desperately that it decided the grammar must be wrong. It essentially said, I know meals can't eat, but the structure demands an eater, so I guess the meal is eating.
The brain is trying so hard to follow the rules that it breaks reality.
It prefers a grammatical impossibility to a structural failure. It's stubbornly adhering to the rules of syntax, even when the result is just nonsensical.
That is profound. It really makes you question what understanding actually is. So what's the big takeaway here?
I think the big picture is that language processing is this high-wire balancing act. On one side, you have these rigid, efficient rules, like late closure, that let us process speech at incredible speeds.
We need that speed to communicate. If we had to pause and analyze every possible meaning, we'd never get through a conversation.
Exactly. But to get that speed, we have to cut corners. We have to take risks. We guess the structure before we have all the facts. We rely on these good enough meanings. And mostly, it works beautifully. It's a miracle we understand each other at all.
But sometimes we fail to clean up the mess. We leave a little syntactic debris behind.
We do. And we might never even realize it.
It really makes you wonder. We focused on that deer hunting example, where we keep the wrong meaning even after we've supposedly fixed the sentence. If that happens in a simple lab experiment, how often does it happen in real life?
Think about reading legal contracts or political speeches.
Exactly. When you're reading a nuanced news article, or, even listening to this deep dive right now, how much of what you understood is actually just a lingering shadow of your first wrong guess? Are we understanding the world, or are we just understanding a good enough version of it?
It's a humbling thought. We are navigating a complex world with a very fast but very messy processor.
Something to think about the next time you find yourself stumbling over a sentence. Maybe go back and read it a third time just to be sure. Thanks for listening.
It's been a pleasure.
See you next time.